Now that we have seen how we can create a recursive method, let's talk about how we can trace the recursive method. In tracing recursive methods, always trace it line by line and think of a recursive method as having multiple copies of itself. So let's talk about the print stars method that we just created. For that method, we can safely assume that if I call it with n equal 3, I will create 3 copies for the print stars method. And every call will not only create a new copy, but it will also transfer the flow of control to it. So it's going to have the control of the application, just like calling a normal method. So if you are in the main method and you call another method that's in your class or in your application, it's going to give it the flow of control. So that method is going to finish execution first before jumping back to the main method. Now each copy will have its own code, set of arguments, and set of local variables. So if you define any variables inside a recursive method and you call it recursively and it creates those copies will have the local variable that you wrote in your code. But in this situation, those local variables will be independent of each other. For example, if you define two methods, let's say method 1 and method 2, both of them having variable that's called x. Now x is independent from the other x in the other method. So x in method 1 is not the same x in method 2. Same thing applies in here. Recursive calls must completely execute before the control goes back to the previous call. So in recursive calls, you will have a call, then another call, then another call. And once you reach the last recursive call, it will not go back to the previous call unless the method finishes execution. And that's why it's dangerous to get into infinite recursion, because you will never go back to the previous calls and you will never go back to the calling environment, which is most probably going to be the main method, and your application will crash. After completing the recursive call, the control will return to the calling environment, which most probably going to be the main method, and the execution in the calling environment will continue from the point following the recursive call. So if you make a recursive call, let's say in line 7, it's going to go to that method, complete execution, and then go back to the main method, continue execution from line 8, let's say. Exact same thing like calling a regular method. Let's see an example here. This is the power method that we just created, and I made it more simple by saying if the exponent is equal to 0, we will return 1, otherwise we will return the base times the recursive call. So it is the same method, but we are accounting for exponent that's equal to 0, and some may argue that this is even more base case than exponent is equal to 1, and it's just based on what problem you're trying to handle. So will you consider 0 or will you not consider 0? Both cases will be the same tracing, same exact output. So let's see if we call the power method with the base is equal to and the exponent is equal to 3. The first call is going to come to the method here, and we will check, is the exponent equal to 0? In this case, the exponent is not equal to 0, it's equal to 3. I will not execute this code, I will execute this other piece of code. So I will return the base, which is 2, times whatever I get from calling the power method with base equal to and exponent equal to 2. This is going to take me to another copy of my method. Now, is the exponent equal to 0? The answer is no. So I will return the base plus whatever I get from calling the power method with base equal to 2 and the exponent equal to 1. Same thing here, but this time I'll call it base equal 2, exponent equal 0. Now if I come here to this call, I'm calling it with 2 and 0. Since the exponent is equal to 1, I will return 1. So where will I return 1 to the previous caller here? So now this is 1, and this is going to return the base times whatever I got from the previous call, which is 2 times 1. So I will return 2 times 1, which is 2 to the previous call. Now this previous call is going to look at the return that I got, which is here, which is going to be replaced by 2, multiply it by the base, and return it to the previous caller. So I'm returning 4. Now this is going to multiply the base by what I just got, which is 4, which is 2 times 4, and then I will return 8 to my original caller. Let's say it's the main method, for example. Let's see some kind of mysterious method here. I'm calling this the magic method, and it says if n is less than 5, then return n. Otherwise, divide n by 2 and add 1 to it, and then call my magic method with that new n. So what's going to happen if I call it with n is equal to 50? I would like you to pause the video here and try to trace this before jumping into the next slide. Okay, so hopefully you paused the video and you tried to trace it, but let's trace it together. So let's see, if I call it with n equal to 50. Now, is 50 less than 5? The answer is no. So what I will do is I will do this step. I will divide n by 2. That's integer division, because remember n is an integer. I'll get 25, and then I will add 1 to it, which is 26, and I will call my method again with 26. Now, is 26 less than 5? The answer is no. So I'll divide it by 2, I'll get 13, I will add 1 to it. It's going to be 14, and I'm calling my method with 14. Then is 14 less than 5? Answer is no. Divided by 2, it's going to give me 7. Add 1 to it, it's going to give me 8. So I'm calling my method with 8. Is it less than 5? No. I will divide it by 2, it's going to give me 4. 4 plus 1 is equal to 5. I'll call my magic method with 5. Is 5 less than 5? Answer is no. I'll divide it by 2. Remember, this is integer division, so it's not going to be 2.5. It's just going to be 2. I'll add 1 to it. It's going to be 3. I will call my magic method with 3. Is 3 less than 5? The answer is yes. I will return 3. Now, this is not the most practical method in your life, but this is just to get you familiar with tracing. Now, let's talk about recursion versus iteration. A problem usually has more than one way to be solved. So every problem in programming can be solved in many ways. So roughly we can say recursion and iteration will perform the same task. But iteration will keep repeating until the task is done, and recursion will break the problem into smaller chunks of code, solve them individually, and then combine those results. So a recursive solution may be more intuitive to implement in many cases because it mimics how we think, how we approach the problem. So if we think of raising some number to some power, we will think of, if the number is, let's say, 2, then I will multiply it by itself 3 times. So I'll say I will go 2 times 2 is equal to 4 times 2 is equal to 8, and that's it. An iterative solution might execute faster. So which one to choose? Actually, it depends on the problem. Some problems are going to be easier to be solved with recursion. Like, for example, in data structures, tree traversal is way easier to solve in recursion than iteration. Here are some classic examples that are usually solved using recursion: factorial, Fibonacci, towers of Hanoi, binary search. And the most popular one is factorial. So let's talk about factorial and see what it is. If I say n factorial, that means n times n minus 1 times n minus 2 times n minus 3 until we reach 1. Now, by definition, 0 factorial is 1. Let's look at an example. 4 factorial is 4 times 3 times 2 times 1. Isn't this the same as 3 factorial? Because 3 factorial is 3 times 2 times 1. And we are just multiplying 4 by that. You see how we can divide this into smaller problems? So we have a base case, we have a way of dividing the problem into smaller chunks. Since, for example, 4 factorial is nothing but 4 times 3 factorial. 3 factorial is nothing but 3 times 2 factorial. 2 factorial is nothing but 2 times 1 factorial. 1 factorial is nothing but 1 times 0 factorial. 0 factorial by definition is 1. Let's go back to our set of questions. How can I reduce this problem into smaller versions of itself? As we said, since n factorial is n times n minus 1 factorial times n minus 2 factorial and so on, and n minus 1 factorial is nothing but n minus 1 times n minus 2 factorial and so on, we can see a pattern here on how we can divide the problem into smaller chunks. Now, how does the method or the method call make the problem smaller? Remember, we are going to call by n minus 1. Eventually, we are reaching 0, so we are dividing it into smaller problems each time. So n minus 1 factorial is less computation than n factorial. N minus 2 factorial is less computation than n minus 1 factorial, and so on. What should the base case be? N is equal to 0, because remember we said by definition if n is equal to 0 I will directly return 1 without doing any computation. Now, how do I ensure reaching the base case? I will need to eventually go to 0. So I'll start with a positive integer, reduce it by 1 in every recursive call. This is what's going to ensure that I reach my base case. Now let's look at the recursive solution for this. We said if n is equal to 0, we will return 1, otherwise we will return n times the factorial of the previous number. And this is the same as the definition we just talked about. Let's just trace it to make sure that we are doing the right thing. So let's try to call factorial of 3. Remember, factorial of 3 is 3 times 2 times 1, which should give me 6. So let's see. The method says if n is equal to 0, I will return 1. Otherwise, I will return n, which is the number, times factorial of the lower number, which is 2 in this example, and then 1, and then 0. So if I call it with n is equal to 3, since n is not equal to 0, I will not be able to return 1. I will return n times factorial of n minus 1, which is 2 in this case. This is going to create a copy of factorial called with n is equal to 2. Is it 0? No, so I'll return 2, which is n in this case, times factorial of 1. Why 1? Because it's n minus 1, which is 2 minus 1. I'll go to the next copy. Is it 0? No. So I'll return n, which is 1 in this case, and I will multiply this by the return of factorial of n minus 1, which is 0. This is going to take me to the next copy, factorial of 0. This should be n equal to 0 here. So since n is equal to 0, I will directly return 1. Where will I return it? To the previous copy. So I will return 1 to this copy. Now I know this is going to give me 1, so I will return 1 times 1. Return to the previous copy, which is 1. I know this return is 1, so it's going to be 2 times 1. So I'll return 2 to the previous copy. And this is 2 now, and I will multiply it by 3. This is going to give me 3 times 2, which is going to be 6. I don't have a previous copy, so I will return the control to the calling environment, and this is going to return 6. This is briefly how a recursive call work, and this is briefly how we can trace it. And I highly recommend that you go and look at other problems like the ones we talked about, the classic examples like Fibonacci and other factorial examples.